All right, everyone, welcome back. Today, we are jumping into a massive topic, a real cornerstone of calculus, especially for all you IB Mathematics AA students out there, differentiation. So let's get right to it by asking the one question that this entire unit is built around.
You know, the whole topic really comes down to this one question. I mean, if you have a straight line, finding the slope is a piece of cake, right? But what about a curve? The steepness is changing all the time, so how in the world do you measure the slope not between 2 points, but at one single exact instant? Well, that's the puzzle that differentiation is here to solve.
So, to answer that big question, we've got to start from the very beginning. We need to build this idea from the ground up. So, let's dive in with the most fundamental concept of all. What exactly is differentiation?
Okay, at its heart, think of differentiation as a special tool. It's a method that lets us find the gradient, or you can call it the rate of change, of a function at any point we want. And the brand new function we create to do this, that's called the derivative. And that straight line that just perfectly kisses the curve at that one point, matching its slope exactly, we call that the tangent line.
So how do we actually find it? Let's build a little intuition. Imagine you're on a curve and you pick 2 points, and then draw a straight line between them. We can definitely find the slope of that line. But now, what if we start sliding those 2 points closer, and closer, and closer together? As that distance between them, let's call it h, gets ridiculously small and approaches 0, that line connecting them literally transforms, and it becomes the tangent line at one single point. And that right there, that's the big idea behind what we call differentiation from first principles.
And that whole idea we just talked about? Well, here it is, all dressed up in its official mouth formula. This is the limit definition of the derivative. It's really just the rise over run formula you already know, but with this incredibly powerful twist. We're taking the limit as the run, that tiny distance h, becomes infinitesimally small. And that's what gives us the exact instantaneous rate of change.
Now, using that limit formula every single time would be, well, a whole lot of work. Let's be honest, it'd be a pain. Thankfully, some brilliant mathematicians figured out a bunch of powerful shortcuts. So let's check out these rules of the game that'll help us build our toolkit for differentiating way more efficiently.
The first and most important rule, the one you'll use all the time, is the power rule. This is your new best friend for any polynomial. It's super simple. For any term like ax to the power of n, you do two things. 1. Bring the power n down to the front and multiply. 2. Subtract 1 from the original power. That's it. It's clean, it's fast, and it just works. But life isn't always that simple, is it? So what happens when functions get a little more complicated? Well, for functions that are multiplied, divided, or even nested inside each other, we have 3 key rules. Got 2 functions multiplied together? Use the product rule. Dividing them? That's a job for the quotient rule. And for the really important one, a function inside another function, kind of like a Russian doll, you need the chain rule. And remember, don't waste brain space memorizing these. They're in your formula booklet. The real skill is knowing which rule to use and when.
Okay, so we've got polynomials covered, but the world is full of other kinds of functions, right? So let's expand our toolkit and look at some of the other common types of functions you're definitely going to see.
Here are some of the real heavy hitters. You've got your trig functions, sine and cosine, which just cycle between each other. Then you have this amazing one, e to the x. Its derivative is just e to the x. How cool is that? And the natural log of x becomes 1 over x. Like the slide says, there are plenty more of these. But, and this is the great news, they are all in your formula booklet. So really, don't stress about memorizing them. Sooner or later, you're going to run into a messy equation where y isn't just sitting there nicely on one side. For those situations, we have a special technique called implicit differentiation. The main idea is you just go through the equation, term by term, and differentiate everything with respect to x. The one little thing you have to remember is, whenever you differentiate a term with y in it, you just tack on a dy dx at the end. After that, it's just a bit of algebra to solve for that dy dx.
Okay, we have all these rules and tools to find the derivative. But so what? What's the point? What can this thing actually tell us? Well, this is where differentiation gets incredibly powerful. It lets us analyze a function and understand its shape and behavior in unbelievable detail.
So one of the most common things you'll do is find the equation of a tangent line at a specific point, or the normal line, which is just the line that's perpendicular to the tangent. This slide gives you a perfect 4-step recipe. First, find the derivative. That's your formula for the slope.
Second, plug in your x value to get the actual slope number. For the normal, just flip it and make it negative. Third, find the y value. And finally, use all that info to find the full equation of the line. It's a fantastic, reliable process that you'll use a ton.
The derivative also acts like a treasure map, helping us find the most interesting features of any graph, its turning points. We're talking about the peaks of the mountains, the bottoms of the valleys, and any flat spots in between. We call these local maxima, local minima, and points of inflection. And finding them is absolutely the key to understanding a curve's shape.
So how do we find them and tell them apart? Well, think about it. At the very top of a hill or the bottom of a valley, for just a split second, the ground is totally flat. That means the slope, our first derivative, has to be 0. So that's how we find them. But to know if it's a peak or a valley, we need the second derivative. This tells us which way the curve is bending. If the second derivative is positive, the curve is bending up, like a positive smile. That gives you a minimum. If it's negative, it's bending down, like a negative frown. That's a maximum. And if the second derivative itself is 0, that's where you might have a point of inflection, where the curve changes how it bends.
All right, it's time to put all the pieces of this puzzle together. We're going to use everything we've just learned to see the derivative in action, both for sketching out graphs and for tackling some real-world problems.
So imagine you're in an exam, no calculator, and you have to sketch a graph. Don't panic. The derivative is your ultimate guide. You just need a checklist. First, find where the graph crosses the axes, the intercepts. Second, use the derivative to find all those critical points we just talked about. And third, find any asymptotes. Those are the invisible lines the graph gets closer and closer to but never quite touches. With those 3 things, you can draw a really accurate sketch.
And let's be clear, this is not just about drawing some curves on a page. Differentiation has huge applications in the real world. The classic example is kinematics, the study of motion. The rate of change of an object's position, or its displacement, is its velocity. And the rate of change of its velocity, that's its acceleration. So the derivative beautifully connects position, velocity, and acceleration. This means acceleration is the second derivative of displacement, which tells you all about the concavity of the original position time graph. It all connects.
When you really boil it all down, differentiation is the mathematics of instantaneous change. It's a language we can use to describe how things are changing at any given moment, from the speed of a rocket to the rate of disease spreads to the change in a company's profits. So I'll just leave you with this thought. The derivative is the language of change. What change would you like to describe?